Swayam Prabha. Digital India. Educated India.
Good morning. Today we will talk about the role of crystal structures. So, we have already discussed about the material properties, particularly the mechanical properties and the nature of atomic bonding. So, now what we are going to focus on is actually how these atoms are assembled into a solid structure, and then what does it manifest in terms of the material properties, because these material properties there are various types of structures which will generate different types of material properties. So, how does, for example, the density depend on the structure? As a case study we will see. So, we will first of all look into the structure of the solids, and then we will see material properties that get manifested from the solids. Now, here we will come to a very important topic which we have to know a little bit, that is called the crystallography, which is nothing but the study of the atomic and molecular structure. This study of crystal geometry, particularly because we will be working when on ceramic materials and metals actually, which shows much more regular crystal structures. This will help us to interpret the relationship between atomic structure and properties of these materials. Properties, for example, the mechanical properties, the electrical properties, magnetic, optical and metallurgical properties. Now, all these things happened starting from somewhere around, I would say, 1867 to around 1915 or so. The very basic developments towards identifying the crystal structure of a material took place after the discovery of X-ray and the application of X-ray in terms of X-ray diffraction, which today very popularly is known as XRD testing. So, what is this XRD testing actually? How to carry out X-ray diffraction test. So, here I will try to explain it with the help of a beautiful video from the University of Washington, the Center on Materials and Devices for Information Technology Research. So, let us look into this, and then we will explain you that how you can carry out a X-ray diffraction testing. So, as you can see here, this is actually a close up view of a X-ray diffraction testing machine. Of course, when the window of the machine is open, because otherwise X-ray is very dangerous. So, a very close up view, and as you can see that there are three important elements there. The left side, which is right now as you can see the left part of it, that is from where the incident X-ray is coming, and the center you have the sample, and the right side you have the receiver. So, that is what is the overall system. Now, let us look into the video, which will give us some idea about how this system actually would move. So, to begin with, you must have a monochromatic X-ray source, and in this case, as you can see that the X-ray source is coming out of the system from a tungsten filament, and it is going to a copper target, and the X-ray is passing through a beryllium window. It is designed in such a manner that you get a monochromatic X-ray source. This monochromatic X-ray source is coming to the sample, and from the sample it is going to the detector. Now, as you can see here that the wave is coming from the sample, and from there it is going to the detector. There is a certain ratio of the angle which is important in order to detect the crystal lattice planes. Basically, the whole thing works in such a manner that as you are having a regular crystal structure, the distance, regular distance between these lattice planes, that works in terms of the diffraction of the crystal. So, that actually generates what you call constructive interference in the system, and by looking at that constructive interference, we actually find out that what is the kind of the crystal structure, okay, if at all it has a crystal structure. So, thus every solid material can be subjected to this XRD testing, and we can find out that first information whether it is crystalline or not. Okay. If it is crystalline, there can be another variation that it may have actually many crystals, not a single crystal. So, these are called the polycrystalline systems, and there are some systems where you will not get a regular order of crystal lattice, and hence these are actually amorphous systems for which you will not be able to observe the typical peaks that you will see corresponding to crystal lattice structure in the crystalline or polycrystalline material. So, these are called amorphous structures essentially. Okay. So, why we use X-ray to do these diffraction techniques? It is because that the wavelength of the X-ray typically matches with the crystal plane separation distance. So, it is between that 1 to 100 angstrom kind of range, and hence X-ray can be used to resolve this picture, and the Bragg's Sir Bragg and his father, they are the people who got Nobel Prize in this direction, and they are the first people who could actually make, of course, before that itself the XRD was discovered, but they can make a connection between the two dimensional reflection that they are getting from these crystal lattices and the three dimensional structure of the crystal. So, which actually later on revolutionized our understanding of the crystal structures. So, that is what a little bit of history and genesis of X-ray diffraction, which is so important for us to determine whether a structure is crystalline or not. Now, formal definition. So, crystalline solids, how do we call a crystal a solid to be crystalline? If you get a long range structure so that the atoms are arranged into unit cells, and the unit cells repeat in a regular orderly pattern forming a three dimensional lattice, then it will be a crystalline solid. And naturally, if they get arranged in a regular pattern, then they will have actually directional properties, like it will be anisotropic in nature. Also, you will see that such systems will have a sharp melting point, and there are many examples of it. For example, gold, silver, aluminum, many of the metals, they are the best examples of the crystalline solids. Now, it is not only that it is only observed in the metals, as told you that many other structures which has ionic bond, they also show very good crystal structures, and among the covalent bonds, for example, diamond also show very good crystal structure. So, there are two types of, I told you that a material can have a single crystal structure, that means it will have only one grain, and that grain itself, every grain we typically say has one crystal structure. So, if there is a polycrystalline structure, then there are many grain boundaries around it. So, only one grain, no grain boundaries, and it is generally formed by a very uniform cooling of liquid material. There are various techniques towards this, and it will have a high degree of order throughout entire volume of the material. Development of a single crystal structure is quite an art on its own, but it has very practical applications. For example, one practical application is in terms of all these computer industries, because the silicon chips that are developed, if you make the silicon chips of polycrystalline structures, then the grain boundaries will add to the noise. So, the microprocessors would not work properly. On the other hand, if you can make a single crystal structure in which the grain boundaries are absent, then this type of structures will be very good in terms of processing, etc. The processing time will be much faster. So, it is one of the drive for the single crystal structure actually comes from the silicon industry itself, the which actually manifests in terms of the computer industry. The other one is in terms of aircraft industry. For example, I told you that creeping is a very crucial mechanical problem for turbine blades, which operates at a very high temperature and along with that a high stress level. So, creeping is a very critical problem in such cases. Now, creeping takes place by the grain boundary sliding. Okay. So, if you can develop single crystal turbine blades, for example, Ni based the superalloy gas turbine blades, a single crystal of nickel or single crystal of titanium blades, these are actually very good in terms of creep strength. So, that is where is another application of a single crystal structure. A typical example of a anisotropy of a single crystal structure, if you consider for example, a BCC structure of iron. What is a BCC structure? We will come discuss about it very soon. You will see that along one edge it is about 125 gigapascal as the modulus of elasticity, whereas along the diagonal it is about 272 gigapascal. So, what it means is that the BCC structure of iron is extremely stiff along the diagonal direction, whereas in the any one of the edges it is actually much more flexible. So, thus it will be if you develop now these a single crystal iron structure, you will see a particular direction where actually it is very stiff. So, that actually gives the anisotropic property of a single crystal. Now, let us come to the polycrystalline solids, because this is actually much more practical, because there are always impurities in a material. So, they are basically as I have mentioned here, that they are aggregate of many small single crystals. They are also called crystallites or grains. So, if there are grains, then there will be boundaries of the grains, which will be responsible for the deformation behavior, okay, the stiffness and many other properties like the electrical properties, the resistance, etc. Everything depends on the grain structure and the grain boundary. Now, it is the grain boundary where the orientation of the crystal will be changing, because you will be having another crystal formation. So, thus the orientation will be changing. These grains are generally in the range of 100 nanometer to 100 micron. Naturally, the larger the grain structure, the stiffer will be the structure, but it will be more anisotropic. Now, polycrystalline materials have a high degree of order over many atomic or molecular dimension. So, they are less than 10 nanometer. If they are in diameter, they are actually known as the nanocrystalline materials. So, they can be nanocrystalline or microcrystalline or even at the macro range. Now, most of the engineering materials are actually polycrystalline in nature, and their properties may or may not vary with the direction. Why? Because the crystals that are indeed going to give anisotropy. So, a single crystal or a which is inside a grain will give you an anisotropy, but since there are many grains and hence there are a random distribution of anisotropic property. So, this kind of get averaged out, and it can give you if there is no grain or direction kind of a orientation in the grain direction, it may give you an isotropic property. So, as an example the common steel is actually polycrystalline, and if the grains of these polycrystalline materials are textured due to rolling, then it will become anisotropic. Okay. But if it is the grains are random, then it will be isotropic. So, this also tells us about the significance of the manufacturing process that it will be subjected to. So, thus a polycrystalline solid may or may not show isotropy depending on the manufacturing process. Now, we have talked about single crystal and the polycrystal. So, naturally the last in the line is where you will not get a long range order at all. That means, the atoms or molecules are arranged in an irregular manner. So, you will not get any periodic packing in such a system, you will not see any directional property in such a system. So, they are basically isotropic because of this reason, and this can occur due to two reasons. One is that, as I told you, that the cooling process actually can govern that whether you get enough time for the liquid to change to solid phase such that the regular the lattice formation is possible. So, with a very low cooling rate, you can even make metals as the glass, and we call them to be met glass. Okay. So, I will talk about different types of metallic glasses, okay, or something like BMG, bulk metallic glasses. They are becoming very important in today's context. So, this is one way. By controlling the cooling rate, if it is the cooling rate is actually very slow, you get crystalline structure, but if you make the cooling rate to be very fast, then you get the glassy structure out of it. So, that is one way of generating this amorphous structure. Of course, the other things are at a later stage we will talk about it, that is the polymeric chains. The polymers are by nature they are amorphous in nature, because depending on what are coming in the cross chains of a polymer, it may never actually show a long range order. So, there are some materials which are by nature amorphous, and there are some materials which are by nature crystalline, but you can force it to take an amorphous structure. For example, this bulk metallic glass or the metallic glasses. Now, let us first concentrate on the structures which has a regularity or a regular crystal structure. So, the way to look at it is to look at something which is known as the unit cell, okay, which is the smallest block or geometrical figure from which the crystal can be thought of that it is built up by repetition in the 3 dimension. So, this unit cell, or so to say the basic structural unit or the building block of the crystal structure, it can be constructed, basically a crystalline solid can be constructed from a unit cell along with a translational operator. For example, you can see that this is a unit cell, suppose a cubic unit cell, and if it has translation only along one direction, you get a particular type of structure. If it has translation in 2 directions, you get this type of a structure. If it has translation along all the 3 directions, you get this kind of a Rubik cube structure. So, thus unit cell with a translational operator will actually develop the complete solid structure. Now, in a 3D unit cell, how do you define the unit cell? There are 6 parameters to define a unit cell. Okay. So, these 6 parameters are what? There are 3 vectors A, B, C's, as you can see, each one of these vectors A, B and C are to the 3 directions. Okay. So, x, y, z, and these directions need not be perpendicular to each other. Okay. So, these are the edges along the edges of the crystal lattice. Only in a very special case, in some of the special cases, the angle between them will be 90 degree. Otherwise, we can assume them to be as generic like alpha, beta and gamma. So, alpha, if you consider to be any angle between B and C by definition, beta is angle between A and C, and gamma is the angle between B and A. So, this is what is the 3 angles alpha, beta and gamma, and these A, B, C's, they define a generic 3D unit cell. Now, from there one more point we have to keep in our mind, that there are 2 important things here. One is called the lattice and another is called the basis. What is the lattice? It is an array of points in space in which every point has identical environment with respect to all other points. Okay. For example, this is a lattice structure where every point has an identical environment with respect to the other points, and the basis is actually the single atom, okay, or a group of atoms identical in composition and orientation in space. So, a crystal structure has 2 parts of it. One is the lattice. The same lattice can have different types of bases actually, and thus can have different types of crystal structure. So, the crystal structure consists of the basis and the lattice. So, with this background, if we go to the types of lattice, then the first generic lattice is called the triclinic lattice structure. Now, in the triclinic lattice, these edges A, B and C, they are not equal to each other, neither the angles alpha, beta and gamma. So, when you have no similarity between the angles and the edges are not same, okay, then you get the most generic system, which is known as the triclinic system, and you can find out through geometric relationships, you can find out what is the volume of a triclinic system. From there, if you bring a little more symmetry, you can get a situation where A, B, C are not equal to each other, that is fine, but at least alpha and gamma are 90 degree. Okay. So, alpha and gamma are 90 degree angles, okay, and beta is not 90 degree. So, then you get a structure which is known as a monoclinic structure. Now, if you get a structure where alpha, beta, gamma all are 90 degree, but still A, B, C are not equal, then you get a structure which is known as orthorhombic structure. Gradually, we are introducing more and more symmetry into the parameters. So, what if A, B, C are all equal and alpha, beta, gamma are all 90 degree, then you get the simplest structure with called cubic structure. What if A, B, C are all equal, but alpha, beta, gamma are not equal to 90 degree, then you get a rhombohedral or a trigonal structure. What if A and B are equal, but they are not equal to C, but alpha, beta, gamma equals to 90 degree, you get a structure which is known as a tetragonal lattice structure. And what if A and B are equal, but they are not equal to C, just like tetragonal, and alpha and beta are only 90 degree, but gamma equals to 120 degree, then you get a structure which is known as hexagonal lattice structure. So, at least we have defined about 7 structures. Okay. So, that means triclinic, monoclinic, orthorhombic, cubic, rhombohedral or trigonal, tetragonal and hexagonal structure. So, these are the 7 basic crystal systems, that is what it is called. Okay. The 7 basic crystal systems, and if you summarize, you will once again see each one of them with cubic structure having the highest degree of symmetry and triclinic having the lowest kind of symmetry in the structure, where neither A, B, C are equal nor alpha, beta, gamma are equal or not at all, they are orthogonal, etc. So, that is what is a kind of all the things, a generic map together. Now, let us look at some of the crystal structures. Okay. Out of these 7 crystal structures, we will take only 3 or 4 of our interest, which we generally find more in terms of the materials that we use. Okay. So, let us first think of the simple cubic structure. Okay. Now, naturally in the cubic structure, if you look at it very carefully, you will see that it consists of 8 corner atoms, 1, 2, 3, 4, 5, 6, 7, 8. So, there are 8 corner atoms, and basically since each atom is shared by the neighboring lattice, if you look at it, there are 6 lattice. If you consider each one of them, then each direction, like this direction 1, there it is getting shared, it is getting shared in this direction 2, it is getting shared in this direction 3, it is getting shared 4, 5 and 6. So, like that there are 6 directions. So, its coordination number, okay, that means the number of atoms immediately surrounding a central atom is actually 6. So, that is how is the coordination number. This type of atoms, if you try to find out what is the packing, that means number of atoms per unit cell, then you can do it in this manner, that already that there are 8 atoms, okay, and also that each one of the atom has 1/8 way of contributing to the whole thing. So, the N is unity, and the atomic packing factor, how do we calculate it? It is like you have the it is basically volume of atoms in a unit cell, okay, divided by that unit cell volume itself. Now, in this case it is a cubic, okay, lattice. So, you know that if the cubic lattice one typical geometric dimension is A, then it will be A cube, that is fine. Now, how do we find out the volume of atoms in a unit cell? To do that, we have to find out how many atoms are there per unit cell and then the volume per atom. Okay. So, in this case you already you can find out that atoms per unit cell is actually the number of atoms, that 1/8 into 8. So, it is effectively 1, and the volume per atom you can consider it to be a rigid spherical system without much loss of generality, and you can find it out that in terms of this packing it will be 4/3 pi r cube, where r is half of the A, half of the lattice distance. So, the packing is something like 0.52 or 52% of the space. So, that means in the cubic structure, cubic crystal structure, 52% of the space is only occupied by the atoms and the rest are actually void or interstitial space. This is a really very poor packing, okay. Something like materials like polonium shows this kind of a packing system. Let us go to a system which is slightly more packed. The next example is BCC, body centered cubic structure. It has actually 8 atoms at the corner, 1, 2, 3, 4, 5, 6, like that. It has 8 atoms if you consider the other corner, 7 and the other one which you can't see. So, 8 atoms in the corner and 1 body center atom. The center atom is not shared by any other unit cell, but all the other atoms are shared. So, basically if you consider the number of atoms per unit cell, then 1/8 into 8 for those atoms which are shared plus the central atom. So, you will get the N as 2. So, then the atomic packing factor, how would you count it? In this case you will see that the atoms per unit cell is 2, and once again it has the basic structure which is cubic. So, it is A cube as the volume of the unit cell, and you can find out from geometry, if you look at this entire structure, you can find out that in the most compact condition the volume per atom is 4/3 pi times the root 3 A by r. That means this volume is actually this distance is root 3 A, hence this root 3 A by 4 cube. So, that if you calculate, you will see that this ratio will come out to be 0.68. That means 68% of the space is now occupied and 38% space will remain as a void or as an interstitial space. So, compare this with a simple cubic structure which has only 52% space. So, naturally this is a much more compact system. Let us look at another structure, and that is face centered cubic structure, FCC. In this case you have the center atom which is not shared, and you have the face centered atoms also. So, if you look at it, that you have the corner atoms which are giving 1/8 into 8, because you have 8 corner atoms, and then you have atoms at the face center, each face center. So, that is actually 6 into half. So, if you consider all of them together, you will get the number of atoms per unit cell to be 4. And then if you again calculate the whole thing, you will find out the ratio to be 0.74. That means 74% of the space is occupied and the rest 26% is void or interstitial space. So, this is definitely much more packed than even the BCC. So, something like materials like aluminum, copper, gold, lead, nickel, platinum, silver, they all of them show the FCC structure. In fact, some materials can actually change their crystal structure with respect to temperature. So, there is a phase transition and the crystal structure change can occur in materials. Best example is iron itself. We will see that. Now, the last packing structure which is also important for us is known as the hexagonal close packing structure or HCP. HCP has a AB kind of a stacking sequence, but this stacking sequence is such that now you do not have one type of a plane. You have A type and you have B type, again A type and then B type. That is how you are stacking each one of them. So, in such a case the number of atoms per unit cell will come out to be n equals to 2, and if you calculate the volume you will see that this is about 0.74. That means 74% of the space is occupied and only 26% is free. So, that means this is the densest most dense stacking sequence. Okay. And materials which shows this is magnesium, okay, cobalt, zirconium, titanium, beryllium, zinc, cadmium, like that. Interestingly, some of these materials are also very high in terms of density. For example, titanium is much more dense than steel itself or iron. So, that is possibly due to the hexagonal close packing structure. How to actually calculate the theoretical density? That is a very interesting way. We can actually do it, and one can show that for metals it matches more or less with the entire estimation of the system. So, how do we do it? You need to know two things to do it. So, density is basically mass per unit volume. So, you have to calculate the mass and then you have to calculate the unit volume. So, how we can do it? The volume per unit cell, okay, for different crystal structures, and that what is the packing structure for a particular material. So, Vc is known to us. Now, how many atoms can you expect per mole? That is also defined by the Avogadro's number. So, we know that. In terms of the number of atoms, you have the number of atoms per unit cell. Okay. So, and also you have the atomic weight, okay, which gives you the mass in terms of gram per mole. So, you have the atomic weight as gram per mole, okay, and you have the Avogadro's number as atoms per mole you are dividing. So, this mole and mole gets cancelled, and what you are getting is something like a gram per atom. So, per the each weight of each of the individual atoms you are getting. Now, you have the number of atoms so that you multiply by the weight of the each individual atom, you get the total weight of the system, and the volume. So, you should be able to calculate the density of the system. Let us try to use it for a simple material like copper. Okay. Copper structure is FCC, and it has you can find out that FCC has 4 atoms per unit cell. Now, what is the atomic weight of copper? That is 63.55 gram per mole. And what is the atomic radius? That is about 0.128 nanometer. From X-ray crystallography and such things, you can find out that what is the atomic radius of a system. Now, what is the volume of the system, because what is the A to R relationship for an FCC structure, and since R is already known to you, so you should be able to find out A. So, you should be able to find out what is Vc, and you will see this Vc will come out to be 4.75 into 10 to the power minus 23 cc, a very very small volume, but nevertheless we are talking in the crystal structure level. So, we know the volume, okay, and you also know the weight. So, if you calculate, you will see the theoretical density will come out to be 8.89 gram per cm cube. In fact, the density of the copper, pure copper, is about 8.94. So, that means our theoretical density calculation is quite close to what it should be in practice. So, that is how we can see that what has contributed to this density of atom. The crystal structure has contributed to the density of atom, other than all other things like atomic weight, atomic radius, etc. So, thus if you know the crystal structure, you can actually predict that what is the kind of density that you can expect from a particular structure. Now, the density of various material classes, if you have a look at it, you will see that in the high density region you will mostly see most of the metals, okay, like tungsten, gold, lead, they are having very high density, then titanium, aluminum, beryllium, etc. And a similar type of density I will talk about it in terms of ceramics that a later talk. They are also, you will see that they are also comparable the density wise, but if you look at the polymers, they really have very low density, because you see they have amorphous structure. Since they have amorphous structure, so they have very poor packing, and since they have very poor packing, no wonder that even though they consist of some of the very similar atoms, but they have a very low density. So, that is why we say that metals have higher density, because it has close packing, and also individual atomic masses are generally more. Ceramics have less dense packing in comparison to the metals, okay, and polymers have the poorest packing. That is why they are amorphous, and hence you see that their density is much lower. And composites, since they are mixed of these things, so they are somewhere in middle, because they may have some ceramics and some polymers. So, that is why they are somewhere kind of an average property you will see in the composites. So, that is how typically from the structure, the crystal structure, you can actually predict that what is going to be the density of the system. So, this is where we will close today, and in the next lecture we will learn the significance of crystal structure further, and something very important to describe such a system, which is known as the Miller indices. Thank you.